All right, this next section talks about the integral test, but really the reason we introduce the integral test is to talk about the p-test, or some textbooks call these problems p-series. And here's the basic result that we need for this section. The sum from 1 to infinity of 1 over k to the p power, this series converges if p is bigger than 1, but it diverges if p is less than or equal to 1. Let's look at two examples that we've actually talked about before. If p equals 1, we have the sum from k equals 1 to infinity of 1 over k to the first power. That is just 1 over k. That is 1 plus a half, plus a third, plus a fourth, plus a fifth, and so on. And we've already shown you that this particular series diverges, but this test also shows us that it diverges because it says if p is less than or equal to 1, the series diverges. Similarly, we looked at p equals 2. That would be the sum from k equals 1 to infinity of 1 over k squared. Remember, p is the exponent. That's what the p is. And this would be 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared, and so on. And we told you in a previous video, not only does this converge, we actually know its sum, it's pi squared over 6. In any case, though, p in this case is 2, and 2 is bigger than 1. So this test would show us that indeed this series does converge. So let me use the integral test to show you where this rule comes from. The integral test basically says if you have a series, integrate the term. If the integral converges, so does the series. And if the integral diverges, so does the series. So rather than looking at the sum from k equals 1 to infinity of 1 over k to the p power, let's integrate that. Now, to make the integration a little bit easier to follow, I'm going to change the k to an x. So let's integrate 1 over x to the p power, dx, from 1 to infinity. If k started here with a different number, you would just start the integral at that number, whatever it was. So this is just the integral from 1 to infinity of x to the negative p power dx. That is, x to the negative p is just 1 over x to the positive p. And that's an easy integral. That's just a power rule problem. That's x to the negative p plus 1 over negative p plus 1, where now I have to plug in 1 and quote-unquote infinity. All right, so here's where I need to think a little bit. If this exponent is negative, this term will move to the bottom. And when I plug in infinity, 1 over infinity will go to 0. But if this exponent here is a positive number, well then when I plug in x equals infinity, that's going to go off to infinity. So for the integral to converge, I need minus p plus 1 to be less than 0. That is, I need this exponent to be negative, which moves the term to the bottom, and then when I plug in infinity, it goes to 0. But that means I would need negative p to be less than negative 1. Just subtract 1 from both sides. And finally, divide both sides by negative 1, but you're dividing an inequality by a negative number, so don't forget to flip the sign. This will tell you p has to be greater than 1, which is exactly what we have written down here. That is, the integral will converge as long as p is greater than 1. So the integral test says, okay, so the series will also converge as long as p is greater than 1. But otherwise, That is, if p is less than or equal to 1, the series diverges. In the next video, we're going to do a whole bunch of problems really quickly just using this one fact. Stick around for that.